XR 会議2020にご参加いただきありがとうございます。XR 会議2020はダイヤモンドスポンサー、シンク&センス、他スポンサー各社の提供でお送りしています。セッション開始まで今しばらくお待ちください。まもなく次のセッションが始まります。コメントは配信画面右のコメント欄からお寄せください。また、スクリーンショットや SNS への投稿に関しては、サイト上部の記載をご確認ください。時間となりましたので、セッションを始めます。コメントは配信画面右のコメント欄からお寄せください。また、スクリーンショットや SNS への投稿に関しては、サイト上部の記載をご確認ください。それではどうぞ。
My name is Brent Insko, and I'm lead XR architect at Intel and the working group chair for OpenXR. I'll start by discussing what OpenXR is, why we needed yet another standard, and where we are today. OpenXR is a royalty-free open standard that provides high-performance access to augmented reality and virtual reality platforms and devices. As a note, I'll be using the term XR throughout the talk, which include AR and VR and MR and any other similar technologies. OpenXR handles communication to and from an application and an XR platform or device. An XR platform provides the application information such as the head and hand position information about the controllers and the input state such as whether a button has been pressed or released, and also display configuration and form factor information such as whether there is a single display or multiple displays. The application provides the XR platform an image or images to display, audio, and also haptic responses, such as vibrational responses in controllers. Before OpenXR, an application developer would have to program each platform's proprietary API. This becomes a daunting challenge as you support more platforms, both from a development perspective, but also a validation and testing perspective. OpenXR enables application developers to program to a single, common, high-performance API, which supports a number of different AR and VR platforms. OpenXR contains everything an application needs to drive XR devices in a system, including device discovery, event processing, sensor tracking, and pose calculations on the input side, and frame display timing and composition, plus haptic controls on the output side. OpenXR is used alongside a rendering API such as Vulkan to generate imagery. OpenXR can be used with any 3D API, but a new generation API such as Vulkan is particularly well suited to create applications with high rendering performance and a low latency that are so vital for a compelling XR experience. So this is a high-level overview of a possible OpenXR application, and it's just to give an example of the flow of the program and the steps involved. We don't have time to get into the details today, so I encourage you to check out our GitHub repository and member company sites for sample code to start from. This July, we gave a one-year update after the release of the 1.0 specification at SIGGRAPH last year. We have launched the OpenXR adopter program and open sourced the conformance test suite on GitHub. We have a number of OpenXR conformant platforms and additional developer preview implementations. And we have also released hand and eye tracking extensions for advanced user interfaces. So now I'll talk briefly about the latest developments with OpenXR. In October, Unity announced upcoming OpenXR support by the end of the year on partner platforms, with further support coming early next year for all conformant OpenXR 1.0 runtimes. Also in October, the Blender Foundation, the organization behind Blender, the free open source 3D creation suite, has joined Khronos. This enables them to help shape the future of OpenXR, Vulkan, GLTF, and many other Khronos APIs. We also have two new conformant implementations. We have the Oculus Quest 2 and the HTC Vive Cosmos. Given a current implementation status update, we currently have conformant implementations including the Microsoft HoloLens 2 and all Windows Mixed Reality headsets. For Oculus, we have the Rift S on the PC, as well as the Quest and Quest 2 all-in-one devices, and we have the HTC Vive Cosmos. For developer preview implementations, we have Valve with a preview implementation on Steam VR. We have Vario with their various headsets, and we have an open source implementation named Monado, provided by Collabora. With these initial conformant devices, we can really show off the flexibility of OpenXR. We have devices that cover both AR and VR. We have devices that are tethered to a PC, as well as all-in-one devices. And we have devices that support Android as well as Windows. By the end of the year, OpenXR will have wide support across game and rendering engines. Unreal Engine has supported OpenXR since last year and has since released improvements around performance and mixed reality capture. Blender has supported OpenXR since its 2.83 release in June, using OpenXR for VR scene inspection. And as mentioned earlier, Unity support is coming very soon. It's still early days for game support for OpenXR, but Microsoft has announced that Minecraft's new Render Dragon rendering engine is building its desktop VR support on OpenXR. OpenXR has been integrated into Chromium, the open source browser project, and with release 81, OpenXR is the default backend for WebXR support. This enables Google Chrome and Microsoft Edge browsers to use any OpenXR compatible device. We've also released, as I mentioned earlier, cross-vendor OpenXR extensions for advanced user interfaces, including hand tracking and eye tracking. And to give a bit more detail on the OpenXR hand tracking extension, it's a multi-vendor extension which enables applications to render fully articulated hands in XR experiences and to use these virtual hands to interact in XR. It includes all the major hand tracking solution providers in XR on the same standard and includes support for a wide range of hand tracking technologies, such as optical hand tracking from Ultraleap, Oculus, Magic Leap, and HoloLens, as well as controller-based hand tracking, such as the Valve Index and Oculus Touch controllers. There is also an experimental overlays extension. This extension allows overlays apps to insert their content into another application's world. This extension was added to OpenXR in version 1.0.8. Developers who want to test out overlays and provide feedback regarding the extension can try it out on Collabora's Monado on Linux, or download the work-in-progress API layer from LunarG and Pluto VR on Windows. LunarG has made the API layer source available on GitHub. We also mentioned briefly earlier the developer preview implementations, and one of which is Monado. Monado is a fully open-sourced permissive license provided by Collabora and community. It's currently passing conformance, though it's not yet a fully conformant implementation, and it supports overlays and has Android support. We also have member companies helping to advocate for OpenXR. Holochip is creating a set of resources for OpenXR developers, which will be accessible on their website. The resources will cover the basics of setting up an application, the OpenXR development environment, including the OpenXR SDK, runtime, device driver, and a sample application. It will also cover modifying the runtime functionality, such as the SLAM implementation, and creating OpenXR extensions. Holochip also offers consulting services in support of OpenXR. So now is the time to get involved with OpenXR. Kronos has open sourced the conformance test and launched the adopters program. We have officially conformant runtimes from Microsoft, Oculus, and HTC. We have preview implementations from Valve, Vario, and Collabora. We have hand and eye tracking cross-vendor extensions for advanced user interfaces and the experimental overlays extension. And OpenXR is being used by real software today. We have Unreal, Blender, Chrome, Edge, and soon Unity and Minecraft support. Thanks, and visit our website for more information.
Hello everyone, and welcome to our class on interaction in OpenXR. The plan for the talk today is to first spend a few moments introducing myself. We'll briefly discuss the basic object handle types in OpenXR. At that point, we'll have the background to explore how OpenXR models interaction. We'll then walk through a sample of actions in the Hello XR application. My name is Ryan Pavlik. I've been working in the VR realm since around 2009. I've been involved with the OpenXR working group since the first official meeting in 2017. I was elected specification editor for the OpenXR working group in 2019. I am a principal software engineer at Collabora, where I work on customer projects in the XR team and contribute to our OpenXR runtime Monado. There are a number of important objects in OpenXR which are represented by handle types. These are the main handle types. All handle types except XR instance have a parent handle type. In OpenXR, destroying a parent handle also destroys all handles that come from it. For example, if you destroy a session, that also destroys the associated spaces and swap chains. If you destroy the instance, that destroys all the handle types shown here, since they all come from the instance. In addition to handles, there are two additional types known as atoms. They're not objects, and they don't have an explicit lifetime. They're just coded numbers that represent some fixed thing in the runtime. The one you'll work with most often is a path. An XR path is a number that corresponds to a string, representing a semantic path. We'll come back to this later. Although these atoms have no explicit lifetime, they only have meaning in the instance they're retrieved from. Do not save or reuse these between runs. An important part of immersive technology is interaction. Before we get into the details of how an OpenXR application is structured, let's take a few minutes to look at how OpenXR models interaction, since it might be a new approach for you. OpenXR focuses on the actions that a user takes in your application instead of on the buttons and controllers that are used to perform those actions. This is an important part of the hardware independence provided by OpenXR. In OpenXR, an action is a semantic or meaningful bit of interaction. It's something you do. Grab object and teleport are examples of names for actions. Actions that should be available in a given context or environment are grouped into action sets. For example, you might have an action set called menu, one called gameplay, and one called driving. You can have one or more action sets active at a single time, so you can have gameplay and driving both active. You do not need to duplicate actions between sets or create additional action sets combining others. There are several different types of actions available. Boolean is essentially a button action. It has either on or off. Float actions are for things like an analog trigger. Vector 2 are two-dimensional floats, things like a thumbstick or a trackpad. Pose is a special kind of action that's a tracked object. Frequently, these represent hands. Finally, haptic actions are an output action allowing you to provide rumble or tactile feedback to the user. Once you've established which logical actions a user of your application will make, you can then customize how they actually perform those actions for the hardware that you're testing. This is done using suggested bindings for interaction profiles. For each controller type that you've tested, look up its interaction profile. These are listed in the specification and cover a number of well-known devices. Additional interaction profiles will be added through extensions. For each device you test with, you submit actions and their suggested bindings for the corresponding interaction profile. The suggested bindings are the logical part of the controller that you'd like to use to drive that action, the specific button, for example. You can suggest multiple bindings per action in a call. For instance, both your left and right hands, and thus your left and right controller, could both cause action grab object. The binding path that you'd like to suggest is a hierarchical string like user, hand, right, input, select, click. Here you can see that we are referring to the select button on the right hand's controller, and specifically the click operation of that select button. For the last two path levels, there are naming conventions and standardized names that are detailed in the specification. All of these paths are listed in the interaction profile definitions in the specification. It's important to only suggest bindings for generic profiles as well as interaction profiles matching devices you actually tested. Your application will still be able to run on other runtimes. Those runtimes may automatically map your actions to the controller available. As runtimes continue to advance, you can expect that these rebindings will increase in quality and can be updated independently from your application. They may also provide an interface for the user to customize how the actions are mapped to the controller, and even perhaps share these bindings with other users. Remapping or rebinding can also be done to improve comfort or accessibility to support a wider array of users. This part of the specification design is strongly influenced by the success Valve has found with their similar Steam Input and Steam VR Input Action binding and remapping systems. You will typically set up actions, action sets, and suggest bindings for interaction profiles in a single block of code during the startup process of your application. This model is actually enforced by OpenXR. Before you can use actions in your main loop, you need to make a call to attach your action sets to a session. This tells the runtime that you're all done setting up your action sets, actions, and suggested bindings, that you're going to use them with this session, and that you're not going to change them anymore. This does make your actions and action sets immutable. You can't modify them after this point, and there's a special error code that you'd get if you tried to do that. If you happen to be writing an editor for a game engine, the solution for editing actions is that each time there's a change, you need to tear down the session, the actions, and the action sets, and then recreate them in order to modify them. This seems like a pain, but there's a reason that the action set is done all up front. The main reason is rebinding. We want the runtime to be able to provide the user with the maximum ability to configure how they're interacting with the application right away. To do this, your application must provide the runtime with the maximum information about its interactions as early as it can. That way, when a user launches your application, if you do not have suggested bindings for the hardware that they're using, the runtime can remap the actions automatically, or pop up a user interface that lets them map your specified actions to the hardware that they have available. This would happen behind the scenes and go unnoticed by your application. You just get compatibility. If you are able to add actions and action sets later on during execution, it would then interrupt the flow of your application if rebinding needs to be done a second time. Additionally, if a runtime supports sharing bindings between users, you'd be able to compose a binding that supports all actions only if action setup is done all at once. Otherwise, for example, if there's an action or action set that's only used in the last scene or two of your game, then a community-created rebinding might be incomplete if that scene was not yet reached, or if the scene was on a path that wasn't reached, making it less useful in general. To make this a bit more concrete, I've gone through the sample Hello XR application that's in the OpenXR SDK source and summarized the actions and bindings that are used there. The initialize actions member function is where these get set up, if you want to look at the source code on your own later. All these actions are in a single action set because the application is very simple. Additionally, all of these actions, except for quit session, are specified with what we call sub-action paths. In this case, user hand left and user hand right. The concept of sub-action paths lets the user perform an action with either of two hands, and also lets you know which one hand actually did it. It's similar to the SteamVR input concept of restrict to device, in case you are familiar with that. The quit session action is different because we are not interested in which hand chose to quit session, just that some hand did. We will still suggest bindings for it on the left and right hands, but we didn't specify sub-action paths because we don't need to know the hand that performed the action. The 4 actions in this application represent a variety of action types. We have grab object, hand pose, quit session, and vibrate hand. After creating that action set and those 4 actions, it's time to suggest bindings. There are a number of calls in HelloXR to suggest bindings. I've picked a few of them for 3 different interaction profiles to illustrate some points. This first one uses the interaction profile KHR/SimpleController. Unlike most other interaction profiles, this does not correspond to any particular piece of hardware. Instead, it's a generic lowest common denominator sort of device that can be mapped to a wide variety of hardware. In the case of the simple controller, essentially all runtimes will be able to map these bindings onto their available controllers. There are a few things to notice here. Overall, as you'll see is a pattern, the suggested binding path for the interaction profile, starting with user hand left, will be marked as for the sub-action path of user hand left, and similarly for user hand right. In this application, all actions can be done with either hand, but you would not see the same pattern if you had actions that could only be performed by one hand. Additionally, quit session is suggested for a button on the left and right hand, but since it was not defined earlier with sub-action paths, we do not specify sub-action paths in the suggested bindings. One point about the simple controller is that its select input is Boolean. It only has on or off. We're binding grab object, which is a float input, to /user/hand/left/input/select/click, which is Boolean. This is fine. The runtime will automatically convert that Boolean value to a float one or 0. There are conversion rules that are described in the specification for these common, simple cases. The second example is the Htc Vive Controller. Here you can see that we've bound the grab object action to a different path. That's because the Vive controller has an analog trigger rather than a button simply labeled select. This analog trigger, which is a float, is now being suggested as our binding for grab object. The runtime will not need to convert a Boolean to a float. The grab object action will get something that's not just limited to 0 or 1, but might be anywhere in that entire range. The last example of suggested bindings we'll cover today is the Oculus Touch Controller. The Oculus Touch Controller has a float squeeze input. It can report how hard you are squeezing using a floating point value between 0 and 1. The grab object action will get a value anywhere in that range, just like with the analog trigger on the Vive controller. Additionally, only the left controller has a menu button. So in this case, we're only suggesting a binding for the left hand for quit session, which uses the menu button. We're not suggesting a binding for user hand right, and that's okay. Thank you for your time. Hopefully you found this introduction to OpenXR to be helpful. I've put a number of resources on this slide that you can follow for additional information. If you have questions that I didn't answer during this session, please feel free to drop by one of the community locations for the OpenXR group and leave a note there with your question. I or someone else in the community will be happy to respond to you.
Hello, XR Kaigi. I am Lachlan Ford, and I'm going to be talking about future-proof XR. First of all, before I start, I'd like to thank Brent and Ryan for their wonderful presentations. Brent for taking us through the history and current state of OpenXR, and Ryan for his insightful rundown of the more technical details of the standard. And thank you all for tuning in as well. So what am I going to talk about today? First, I'd like to talk a little bit about myself and my background, and then delve deeper into what I mean by future-proof XR. This talk will be a little more conceptual than the others, but I'll also be diving deep into technical details as well. As mentioned earlier, my name is Lachlan Ford, and I am a software engineer at Microsoft. I work on the mixed reality team, and there I work on HoloLens and Windows Mixed Reality, mainly with a focus in implementation of open standards such as OpenXR and WebXR. And also since early 2018, I've been helping to define and shape the emerging OpenXR spec with the rest of the working group at Kronos. And other than that, I've just been a programmer since forever. So why call it XR? Well, as Brent mentioned, an X looks like a V on top of an A. So it could stand for VR for virtual reality, or AR for augmented reality. But it's more than that. XR is a nascent and emerging technology that is rapidly evolving and transforming. Computing is undergoing a shift towards spatial, and it's impossible to predict what the spatial computing devices of the future will look like. They already take on many forms, from camera pass-through AR on phones and some head-mounted displays, to fully immersive VR and head-mounted stereoscopic AR like HoloLens, as well as projection-mapped cave systems and head-tracked magic window systems. So how do you create a standard that can describe all of that? One which allows the apps that you build now to be compatible with the various forms of XR platforms not only currently available, but also past XR platforms and future XR platforms, as in, how do you achieve backwards compatibility and forwards compatibility? Being able to build a single XR application that is able to target all manner of devices in a backwards and forwards compatible manner is advantageous not only for the consumer, who gets to experience the app on their device of choice, but also developers who can target a much larger audience with far less effort. That was the idea behind many of our design decisions when we created the API. To put it simply, OpenXR is designed to let you build apps that run on many XR systems, leveraging their unique value with the same code. And many of these XR systems do not exist yet. But all this does not come for free. There are some rules that you have to follow to unlock this potential. Now, I'm going to take you through the various parts of the OpenXR API and give some background as to why they're designed the way they were, and also examine a few traps that you could fall into when using these APIs. If you avoid these traps, you are more likely to create future-proof OpenXR applications. The first I'll talk about is form factor. The form factor is important for informing the runtime what class of XR devices your app supports. Currently there are two values in the core spec, which are head-mounted display and handheld display. This is important as the UX for each is very different, and behaviors of runtime will also be very different. For example, the view reference space is located on the display, which for head-mounted displays implies that it tracks with the user's head. But for handheld devices, it would actually track with the device itself, as the display would be on the device held in the palm of the user's hand. A runtime may support multiple form factors. For instance, a phone may be able to slot into a Google Cardboard-like device and become a VR headset. Apps must be responsive to this and change their UX accordingly. Next, I'll talk about view configurations. Each system has its own ways to render, which is partially encapsulated by the View Configuration API. There are general kinds of view configurations, such as mono and stereo, and also special kinds, such as Quad Vario or Microsoft's secondary mono first-person observer. The special kinds require special handling in code, such as extra application-provided data. You cannot assume that a view configuration will be supported based on the form factor. For example, a head-mounted display does not have to support a stereo view configuration, and a handheld device may support a stereo view configuration. Future platforms may have unexpected kinds of view configurations as well, perhaps due to lens and display technology innovations. Thus, the app has to query the runtime dynamically to handle what view configurations the runtime supports. Next, blend modes. For the best rendering experience, the app should query the blend mode for the runtime and prepare its assets for rendering based on what the runtime supports. For example, you do not want to render black for an additive display, as it will appear transparent. Therefore, if you have a VR app that supports shadows, and you want to port that to an AR system, or have that app support an AR system, you will need to handle the shadows differently if it is on an additive display, such that they don't render transparently. And as with previous examples, you cannot assume that the blend mode matches the form factor. Similar to the view configuration. For example, a VR device that supports pass-through AR will return alpha blend and opaque. Next is the session state lifecycle, which is very important to respect. This allows your XR app to conform to the specific application lifecycle of the underlying operating system correctly. And this prevents any lifecycle issues across platforms by standardizing this at the API level. Next is spaces. It's important to note some reference spaces are optionally supported. For example, the stage reference space is currently not supported on HoloLens. As I mentioned earlier, a very common mistake that I see developers make is using the view space to find the location of the head. This is a mistake, as the view space is not where the head is on all runtimes. For example, in non-head-mounted systems, it will be wherever the screen of the device is. In fact, even on head-mounted systems, the view space origin is somewhere in the region of where the displays are of the system, but it's not in a reliable place on all systems, and so you shouldn't rely on that. Another mistake is using the view space to generate rendering parameters like view matrices and projection matrices. This might appear to work on some runtimes, by virtue of the view space being near where the physical views are, but it will fail catastrophically on other runtimes. The view space is supposed to be used for targeting rays and screen space or view-locked positioning of UI elements. Speaking of generating rendering parameters, the correct way to do it is to always call into the runtime using XR locate views. The runtime will then generate the best rendering parameters which your app should then utilize for rendering. Attempting to generate it yourself is generally a bad idea, unless you are using an extension which lets you augment the data, such as XR Epic View Configuration FOV, which modifies the data in participation with the runtime. Next up is the action system. Now this was designed from the ground up with future-proofing in mind, as XR input devices are constantly evolving and changing. We've seen that just in the last few years, going from simple Vive ones to Windows Mixed Reality controllers to Oculus Touch to the Index Knuckles controllers. There's all manner of shapes and sizes here, and who knows what it's going to be next. Thus, we came up with an abstract verb description system which describes input at a high level instead of describing it at the input device level, which would be an intractable problem given how much the industry is evolving and how much the device shapes and form factors are changing. Interaction profiles are the runtime's way of describing the class of device that it is using, that it can accept, that is powering the actions that the app has described. It is not a direct description of the current device connected to the system that the user is using. As such, interaction profiles are not devices, and you cannot detect the system or the devices that your app is running on by inspecting the current interaction profile. The purpose of the interaction profile is to inform the UX of the input UX of the app based on the class of input device that is used. If utilized properly, describing your input at a high level using the action system will allow all kinds of future devices to be compatible with your app. It would be pretty amazing if in the future, the OpenXR apps which we make today would be compatible with crazy future hardware like brain implants and Neuralinks and those sorts of things. Now, the last thing I wanted to talk about was extensions. When everything else is covered by the core API, what's left is platform-specific functionality. This functionality is unlocked through extensions. Some are multi-vendor, some are single-vendor. The presence of an extension cannot be assumed, and you must always query the runtime for the extensions that support it before using them. Otherwise, your app will not work on systems that don't support those extensions. And that's all I wanted to talk about today. So, in conclusion, OpenXR is a platform-agnostic API that attempts to encapsulate as much platform eccentricities and specifics within runtime implementations. The API is general and largely dynamic, but some specific things are required to be handled. Utilizing the API correctly will go a long way towards future-proofing the apps that you build. This will allow apps to support all manner of past, present, and future XR platforms. This has the benefit of not only increasing platform compatibility, but also decreasing maintenance costs by offloading the work of porting to runtime implementers. To get all this, you must play by the rules and not try and outsmart the API. Fingerprinting is generally bad and will cause your app to not be future-proof. You must also never make assumptions about the properties of the system you are running on. Some things that you might get away with on one system will fail catastrophically on another. Anyway, thank you. Thank you for listening.